Hello, everyone. My name is Asmani, and I will be talking about the high-rate tail-biting list decoder with the dual trellis structure that I implemented this summer. So, as for the table of contents, I will first be introducing the Communication Systems Lab, then going over background information on what communication systems are, then talking about the methods on how I implemented the list decoder, then moving on to a live demo on how I run tests. Then I will be going on to presenting results and then discussing those results in the conclusion and discussion. So what is the Communication Systems Lab? The Communication Systems Lab at UCLA is in the Electrical and Computer Engineering Department. Our principal investigator is Professor Whistle, and our daily lab supervisor for this summer was Beryl Sue. My lab partner was Brennan Towell, and we worked on the list decoder together. In general, communication systems are electrical systems that facilitate data transmission or communication between devices over channels. Applications of this include phone calls, text, Wi-Fi, radio, websites, anything to do with digital communication. And that's why communication systems is so important, because of its applicability. As for a background, the background about communication basics is a little bit abstract. So I will have developed a metaphor for you all to reference. So let's say that I want to send you a message via a piece of paper. The paper has 101 printed on it, and I hand it to you and you receive the message perfectly, 101. Now let's say that there is a paper crusher between us that crumples the paper before you receive it. I give you the same message on a piece of paper, but the paper crusher crushes it into a ball. So when you uncrumple the paper and read the message, the marker is all smudged and the message is completely different. And now you think that I sent you the message LUL. But that is not correct. I want to send you the correct message that I intended to. But how do I send my message to the paper crusher and make it so that you can still read the correct message? Well, maybe I can pass the paper through the paper crusher in a different orientation, so that rather than the paper crusher crumpling the paper, it just flattens it. This seems to work, as the flattened paper message does not get smudged from the crumpling, and then you get the message and it comes through as unaltered. Now let's apply this concept to how digital communication actually works. First, we have an original message of a certain length in binary. This is like the message we have written on our piece of paper. Then this message is encoded in something called an encoder. The encoder changes the message using a type of conversion table called a trellis in order to make the message easier to send over a noisy channel. This is like when we changed the orientation of our piece of paper, so it was easier to send it into our paper crusher to keep the original message. A channel is an electrical circuit that acts as a pathway for a signal that distorts the message. Now, when the message comes out of the noisy channel, it is not only distorted, but it is also not the same length as our original message. In the same way, when the paper comes out of the paper crusher, it is horizontal and cannot be read as it is. The decoder then must remove the noise and revert the message back to its original size to try and match the original message for the receiver. To return to the visual analogy, this is like when you take the horizontally oriented paper and flip it vertically so that you can read the message written on it. It is important for this process to be accurate, for the received sequence to match the original sequence, and it's important for it to be fast because delays in transmission can be annoying for different users. So hopefully this metaphor has shown you the importance of facilitating reliable communication, because in an increasingly digital world, reliable data transmission is crucial for communication. So the first method that we use for implementing the list decoder is called an encoder. The encoder encodes a message, improving communication over a noisy channel. As stated before, encoders increase the size of the message corresponding to the rate ratio, because if we send more bits over the channel, it will be easier to restore the original message even if some bits are changed. More information equals greater likelihood of having a correct message. However, we want our bit message to not be too long, because the more data we have sent over the channel, the noisier it is. So we want to make a high rate code which corresponds to the ratio n-1/n. This can be 3/4, 2/3, and more. Just to quickly review this visual image, this is a 230 encoder. There are 2 inputs, 2 x's, and 3 outputs, 3 y's. Each x variable undergoes various operations in order to be converted to the 3 output bits. The next method of implementation was implementing the decoder. The decoder corrects the message received from the noisy channel and converts it back into the original message using the trellis. The decoder uses a trellis as almost a conversion table to get back to the original message. This is what a trellis looks like. Each state transition going from one black dot to the next requires an input bit of 1 corresponding to the red line or a 0 corresponding to the black line. Each input bit creates a different weight, which is the difference between the output highlighted in purple and the received sequence. After completing the trellis diagram, one can trace through the trellis and determine the path of least weight, which is highlighted in green. The weights will not always be 0, and any weight that is not 0 is an example of errors being corrected, right here, as you can see. This is the hallmark trait of what's called a Viterbi decoder, which decodes and corrects at once. The inputs, the red lines, and the red or the black lines, then correspond to the decoded output. In this case, we have 3 red lines, so therefore our output is 1, 1, 1. Our next method was implementing the dual trellis. So the previous slide showcased a trellis compared 2 bits with 2 bits in order to find the weight difference and create the output. In the single trellis on the left, the 4 bits are compared with 4 bits in order to find the weight difference and create the output. But this special trellis, called the dual trellis, compares 1 bit by 1 bit to find the weight difference and create the output. There are less comparisons overall with the dual trellis, so it is faster. And this is a worked out example of a dual trellis, as I did with the previous trellis. So what's the next method that we have to implement? List decoding. So we have one problem. Sometimes our decoded message is not perfect. Even though the sequence may correspond to the code from the path of the least weight, because of noise distortion in the channel, the message could still not match the original. So we implement a method called list decoding. List decoding first uses a CRC check, which is an accuracy checker, to make sure that the decoded message matches the original message. And then if they don't match, we go backwards to the trellis and find the second best path, which is one divergence from the best path, as you can see in this image. This is the best path and this is the divergence. So we trace back the second best path, determine the output, and do the CRC check again. If the messages still don't match, we now have to find the third best path. We continue with the sequence until our output passes the CRC check. Then we know that we have correctly decoded the message. The method incorporates an algorithmic self-verification, preserving message integrity. So my research project implements a high-rate tail-biting list decoder using the dual trellis. The tail-biting portion means that the starting and ending states must be the same. The dual trellis makes less comparisons, so therefore it's faster and it decreases complexity. High rate means that there's a smaller encoded sequence, which makes it more efficient. List decoding finds the most correct message, which makes it more accurate. And we use C++ to compile all this because it has a faster testing speed. As for the materials, I used C++ because of its advantageous compilation speed, and graphed my results in MATLAB. For the duration of this project, matrices and arrays were utilized to store different states in the state diagram. Code was tested by graphing frame error rate versus signal-to-noise ratio. Frame error rate is calculated using this equation. It is the number of incorrect bits in a given decoded sequence. SNR determines how much noise our channel has. A higher SNR means less noise. Now I will be showing a live demo of how I actually collect data. So this is my dual trellis code. All I have to do is start the code and I get this output. I get a number of trials, which is 1,000, and then I have my frame error rate and my SNR. I will run this multiple times for different SNRs, and then I will record my frame error rate for every SNR and graph it in MATLAB. So now we have results. In the list decoder, a list size of 1, which is the blue line, means it's not list decoding, and list size of 2 means we did one traceback after the CRC check if the decoded sequence didn't match, which technically is list decoding. So the frame error rate on the y-axis generates the number of errors per run in decimal. The FER for list size 2 is less than that of list size 1. This follows with our knowledge because from previous papers, as we stated, implementing the list decoding would increase accuracy. Additionally, as SNR increases, the FER decreases, which makes more sense because smaller SNRs signify more noise as a core modulation generates noise. Finally, conclusion and discussion. So increasing list size offers significant improvements in FER for a given SNR is the summary of our results. And also the use of the dual trellis reduced decoding complexity time taken by 75% compared to a standard trellis for a rate 3/4 system with 2 memory elements. Larger list sizes produce less frame errors in the decoded message at the cost of increased decoding complexity. And here's a picture of our dual trellis and our list decoder once again. Up until this point, a tail-biting list decoder with a dual trellis had not been done with a high-rate code, nor had it been implemented in C++. We confirmed our hypothesis and provide new research into creating more efficient and accurate communication. For further research, larger list sizes may be scrutinized beyond list sizes 1 and 2, which were tested for the purposes of our project. We made a more accurate and fast communication. Any form of digital communication should be as efficient and accurate as possible. Accuracy is important in examples of using a telephone. We would like for the input to match the output, and then efficiency is important to stop website crashes from high traffic. For example, the WandaVision finale caused crashes in Disney Plus because of exceptionally high streaming traffic, causing the website to be overloaded with requests, and it crashed. On the methodology front, it can be challenging to develop critique since the vast majority of this project involved coding and product development. Through a series of experiments for data collection and verification were conducted throughout the research. By creating a high-rate C++ version of the tail-biting list decoder using the dual trellis, my research partner and I have contributed to my lab's main goal, developing practical coding schemes that approach information theoretic limits. Here are my citations that I used in my research. And finally, I'd like to thank all of my colleagues, especially Professor Wessel and my team shown here, for their invaluable guidance and support. Thank you so much for listening, and I am open to questions.